So I think we should start because it's already 5 minutes past
Yeah, sure. 5 minute break,
half
5 minute
past
delay is okay, but
12.
then let us start.
Okay, today we will be discussing how to do packaging in Python and what it really means and how you can actually use it to your advantage. First of all, we need to understand why it is necessary to distribute your work and your stuff. Well, for example, you did a project, you want to share it with people, or you want to, uh, for example, create an application out of it, or you want to actually sell your product. So it's really important to find a way to make your project work in different environments and in different on different platforms. This is a very broad view of what distribution is, and it's entirely void of any detail. But that's the essential part. You want to distribute and share your work. So, and by your work may be a library, an algorithm, or a pipeline to process your images, for example, or data. It can be an application. It can be, for example, some sort of video editing application, or it can be a computer game. So you need to somehow to distribute it. And the idea is the sort of high level idea is the farther you need to go, the farther you need to distribute your software, the more you should actually take and bring with yourself in order for it to work on very remote platforms. By this I mean, for example, imagine you have you need to go to, for example, to a friend's house for dinner. You typically take your wallet with you, and you're done. So you can actually go there. Now imagine that you want to go to work. You take your wallet and some of your belongings in your backpack. For example, you take your papers, or you take, I don't know, your a hat or a scarf. Now imagine you're going hiking. You take your food supplies, you take something you take a flask to drink water, you also take wallet and sweater. Now if you go to another country, yes, or to another city, let's start with the city, you take a small suitcase or a really packed backpack. If you go to another country, you take a luggage, and with that luggage you take all things that you might need, extra clothes, extra medication, stuff like this. So you see, the farther you go, the more you have to package. Now in the realms of computer software, if for example you want to run your project on your own machine, or on another machine that is under your control, you just need to essentially copy its source. Well, if we're discussing Python, if you want to, for example, distribute your project on a cluster which is not under your control, you need to put a little bit more effort into packaging, or into deciding what is essential for your project and what is not, and packing it. If you want to ship it, for example, to a customer for whom you developed, you need to not only do Docker, because Docker is well, you can do Docker, but sometimes Docker is Docker containers are usually quite heavy. So you can try to find the middle ground. You can try to package the necessary libraries, but still rely on the system Python, for example. If you, for example, want to ship it somewhere further, you might try to ship Python inside your package. So you can always find applications where you need to put more and more into your package. For example, ultimately, sometimes it is the customer requires you to ship the whole hardware for example, a dedicated computer with all stuff pre-installed, so they just you can just plug and play it and can play with it. So the more you need to take with you, the larger the package. Sometimes it gets even physical. So this is the whole idea. So we will be discussing today packaging in Python, and we will not going to touch the aspect of making actual application distributions. We will be discussing distributions of libraries. So all the code that you write in Python, in research code or in, for example, your projects, it is going to be library code. But if you want to package a game that you developed in your spare time, this is still useful for you, but we won't be discussing how to actually make it work on other environments like Windows. We will be mostly sticking in Mac Linux-based systems. So okay, so Python project is in general is just a collection of files. For example, let's have a look at the project that hopefully we will have time to work on today. You see, this is a really bad project in terms of organization, but essentially there are scripts. Yes, there is a README, possibly a license, and some files, some resources, I guess. We can have a look at another project. For example, let's have a look at OpenAI Gym. Sorry, this one. You see, this is quite a large project. It has scripts. Well, not so much scripts, but anyway, there's some scripts. It has possibly the library itself, init, core, whatever, and all the structure inside. It also has some, I don't know, I can't see if it has data, but it could have data. For example, it has examples as a part of documentation. It has documentation as part of documentation, yes. So package is not just, well, essentially it's a collection of scripts, but it also has some additional resources, data, and some meta information and documentation. So, but the most core idea is that a package tries to solve some problem. So all these resources are related and relevant to the problem that the package, the project, sorry, is attempting to solve. Now, the idea of packaging is to make it so that your project can be squished into one file that can be reliably transferred, deployed, and used in production environments. So that's what we'll try. So today we'll be covering how to organize a project into a package, how to possibly include external C or C++ dependencies in it, and finally preparing for it for a distribution. So the important distinction between Python modules and packages is only on the file system level, in fact. But there is also, well, by which I mean that, let's have a picture here. A module is just a standalone .py script. That's it. And the package is a directory of packages, of directories, yes, or scripts. So essentially, that's the most important distinction that you actually have to worry about. A nuance is that sometimes, or well, not sometimes, but modules are usually well, programmers in practice usually call modules those scripts which only import from external libraries, not from itself, obviously, and not from the package they reside in. For example, if we let's have a look. No, let's look at OpenGI. OpenAI Gym is a package. Yes, it should, by this principle, not import not only import from external libraries like system Python library or whatever, but also from itself. For example, we can take core.py, and we see that it sort of references itself in a not very standard way, but it still imports from itself errors, utilities, and provides some objects. Okay, so this is just this is not a clear-cut distinction as the file system distinction, but it also helps for more clear understanding of why some things are called modules, some things are called packages. On the system, on Python level, you can import from a package or a module, and you don't even need to know how that import actually did its job. For example, you can, at some point in time, you can first provide user with importing from a module, but then at some point in time, you understand that, well, this module has grown in its functionality, so it needs some organizing, and so you actually create a directory with the same original name as the module, and then you organize stuff inside. But the user will only see this directory, and the user won't even have to change their code because they will just import from that module all things that you provide with that module. User doesn't even know or doesn't care if that module is a standalone module, which is only a pure Python script, if it's a compiled extension, or if it's a package. So on the Python level, there is no real difference. And from the user perspective, that's the same. There is no difference. You can use a script, or you can actually, under the hood, substitute the script with a package. No real difference. So modules serve as basic organizational units, and packages are organizational, sort of like trees of modules. Okay, and may contain like Python modules, extensions, or other packages. So this is the essential structure. The consensus, it's not the consensus, but it is customary to always add a dunder init file into your packages like this, because, for example, certain utilities, when they scan your file system or they sort of perform some analysis, they sort of rely on the presence of this file, regardless of its content. However, it is, Python, there is a semantic difference between a package with a dunder init file and a package without a dunder init file. But it's only semantic. There's no underlying, like you won't be, there won't be a problem for you if you include a dunder init or you don't, or you leave it out. Python will eat it and still work. It doesn't really care. So if you have a dunder init package file in your package root directory, then it is called a regular package, and that's it. But if you don't have, these type of packages are usually called namespace packages. I can't really recall an example of a namespace package, but maybe if we can have a look at distutils, but that's a real package. Anyway, so you can, there is no real difference. If you include the dunder init file, then you sort of declare that it's a regular package. But if you don't, Python will still work, so it doesn't really matter. Now, you might ask, why do I need to, well, if I can just have if my code is in a single file, in a single standalone Py script, maybe with some extra compiled extensions or whatever, why do I need to go through all this organizing and all this packaging if I just can take this file, take the compiled extensions, just zip them and send them to my own container in Docker or whatever. The problem is that this sort of solution tends to bloat. You add one algorithm, you add another functionality, you add a third, you want to add some documentation, and now you realize that your file is a mess of code, documentation, different functionalities, unrelated pieces of of code and stuff like this. So the main problem here is that at first it's hard to maintain. Of course, you alone can maintain it and maintain it for at least, I don't know, a month, until you just forget about it and move on. But then when you come back, you can see and you will start to try to understand the code, and you just feel very frustrated because it's not very organized. So first motivation is for yourself, so that you can always understand that your code is organized. You know that it's organized. You know that if a file is named core, then it probably realizes some core functionalities that you put in there. That's the first motivation. Second motivation is you won't always be around to maintain the code. For example, if you work on a project in a firm, in some software company, you work on a project, but then you switch to another project, then you leave the company and move on, whatever. The people who inherit your project still will have to actually work and maintain it. So it is good practice. It is advisable to organize your work so that it can be easily transferred and shared with others. So that's the second motivation. Well, that's basically it. The third motivation is that it looks nice when it's organized. However, it is yes. If names, for example, let's have a quick look. Okay, let's create a folder somewhere here. Yes. cd mkdir. Let's call it FDS 2020 test. Okay. Distinction between namespaces and regulars. You know what? Let's open another window because I remember that this one had some issues. FDS. We have test. Yes. We see. Okay. Sublime. We open Sublime so that we can see stuff. You see, it's an empty project. Let's create some empty script. Let's call it main.py. Or maybe maybe I do have an example here. Let me have a look. I don't recall it very well. Open. If main of this project, no.
Yo, can we increase the font size?
Where?
On the terminal, for example.
Oh, okay.
Cheers.
Yo, is this better? Yeah, hopefully.
Yeah, thanks.
Cool. Project. Okay, I don't have an example. Let's create an example. It doesn't really matter. Okay, let's make a directory of proj, and let's add a couple of files there. Proj. Let's call it stuff. Okay, and in our development environment, we can see that we have main py and stuff py. Now I can do just straight. Let's write some code in here. Def do stuff, and this stuff will be, I don't know, print stuff. Okay, this is we are creating a namespace package. Import proj. Okay. This is in main. Or we can even try to use interactive Python environment. Okay, so from proj import main, want import do stuff. Let's try this one. It's not going to work because our package has not, we have not organized it properly. You see, it doesn't work. What can we do? We can first, this project, the distinction on the Python level, there's no distinction essentially, but this is a semantic difference. So if we import stuff, we see first of all that a dunder PyCache file has been created, and now we have this stuff. Let's have a look at what this stuff actually contains. Well, it contains our function do stuff. Okay. Now, what else can you do? You see, I imported from project. I imported the module stuff, but I can't import do stuff directly from project. How to? So this is now comes the important distinction between namespace project packages and regular packages. If I add dunder init file, proj init, you see, let's try the same example again. If I import this thing, it won't work because although I added dunder init, nothing happened. Now this is, now you might ask, well, you added the pro, now it's a regular package. What's the difference? You see, dunder init actually is the special file that is run on import, and it allows you to expose some stuff, some code, some functionality that you wrote to import directly. So, for example, in order for this line to work, I need to import from stuff, import do stuff. Hopefully it will work. Python. You see, it doesn't work, and I'll go into reason why it doesn't work, because I did not do it correctly on purpose. In order to do it correctly, I need to put a dot. I will go into detail why the dot is important here. For now, let's I'm just showing you that the main distinction between namespace and regular packages is the content of dunder init file. That's it. So if I stop this and restart it, I can do this, and it works. Now, if we get back to the main presentation, we were just about to actually discuss the issues of that are related to regular packages and namespace packages. So essentially, namespace packages are, you might call them, I would call them legacy, because it doesn't cost you much to add an empty init file, and there is no real difference for Python. They behave the same. Dunder init file just exposes some functionality that you wrote, and right now we will understand how to expose stuff using dunder init. The main idea that we have just seen, well, we're just getting back to relative imports, and I don't know where you got this from, because in order to undo relative imports, you need to actually install the package. But before you install the package, you need to make sure it works, and how to reconcile this difference. And I don't know, well, I heard a completely different practice, and let's see how, for example, scikit-learn does it. Because pygym is not a good example of programming, because a lot of students who don't know any better commit stuff there, and it's just a huge mess of really different code styles and different imports. Let's have a look at, I don't know, Gaussian process with scikit. What it does. Let's call dunder init. From .gpc, it imports. Okay. Import subpackages. First of all, there is legacy about not importing. But if we have a look at the most widely used package in data science, it uses this practice. It doesn't mean, of course, that it's the best practice, and of course you can first try to install your package like in Gym, and then do something like this, like they do. For example, Gym vector, don't care, async vector env. What does it do? It imports from itself. But for this to work, it needs to somehow make sure that it's already installed in the system. For example, if you're developing this, you need to make sure that your project is in so-called editable mode, so that it can be actually referenced from Python's, so that it can be visible on path. Okay. However, I have never encountered any argument that says that, well, or in any situation where relative imports in packages did not work. Of course, unless you have some fiddling with paths, but that I don't know. It seems to me like a very niche or very rare case. Anyway, scikit does it like this. It imports from itself quite regularly. For example, you can see here. Okay, you see this utils. Okay, this utils stuff. You see this? Okay. Scikit imports a lot of stuff from utils. Let's have a look at, I don't know, linear model. Does it import from utils? No. Let's have a look at ensemble. Ensemble forest. And yes, what it does, you see, it has a lot of relative imports, because this is not just a design decision. It just more. It makes your package sort of position independent. Otherwise, your package will need to be installed in order to be work in development, which is somewhat strange. Anyway, of course, you can after that always replace relative imports with absolute imports, and then just copy the project and paste it, and it will work. But this makes it clearer, albeit a bit harder to follow, but clearer. Now, so as you can make have guessed, we're discussing relative imports, and well, relative imports are. I have never, I would not like to repeat, I have never seen an argument against them. That's it. I have read quite a lot, I've seen quite a lot of packages. Maybe there is a reason for that SciPy does it, aside from it being legacy. I don't know, and PyGym, but there is no like clear reason for, well, relative imports do not work in this or that situation. That's it. For me, they worked in many projects that I wrote about, I don't know, I can't count on them, but small, large, maybe about 10 or 20 projects of different size that I wrote. So anyway, in order to import, so from here, from this thing, if I write proj here, it won't work because the my package proj is not installed. But if I leave .stuff here, it will work, even if it's not installed yet. So that's one benefit to relative import. Python is smart enough to understand that dot here means relative to your own position. And the number of dots actually indicates how many steps backwards in the directory structure you need to have. For example, if we have a look at scikit project, again scikit, it's a good example. Tree sklearn, you see, it has a lot of stuff in it. So each dot, for example, let's have a look at let's have a look at what I'm looking at, neural network. Okay, each dot, one dot, well, not here, but sorry, this one, yes. One dot in the folder neural network, in the subfolder neural network, indicates that this file wishes to import from some other module that resides within this directory neural network, say scalar neural network. Two dots instruct import Python import machinery to move two steps within the parent tree. So one dot is for neural network and two dots is for the root of the root package, so the root folder. Sorry. So here, for example, this means that I want to import something called base from a sibling bar. Sibling is like a sibling, let's say, module, sibling object. A sibling object is an object that shares a parent with the current object. See, and this means that we need to move two steps in the parent. So basically, we take a grandparent and take just take whatever the grandparent allows us to see using two dots, and we import some object function there. If I put here, for example, ont or whatever, yes, I will be importing for object ont something called func, but ont will be like the child of the grandparent, but not the parent of the current module. Very convoluted, but maybe a tree diagram would help, like this one. Anyway, the scripts can't do relative imports. So yes, that is why maybe it is sometimes this just doesn't work. So and therefore we have this negative and attitude towards this. But if you put your script into a folder and put some other scripts there, then you can do relative imports easily, provided you do not import that script. Well, provided you import the project, and provided the script resides in not a project in a package, provided that the relative imports will work. However, there is a subtle there is a subtle risk of creating circular imports, which are also present in the cases when you don't use relative imports. So you should be aware of creating circular imports. By which I mean, for example, here in our toy project, I have stuff here. You see, and if I create let's call it proj other pi. Now, if I take if I do import dot stuff, sorry, from import do stuff, yes, and then here I declare def func as an empty function, okay, funct. If I do it, if I actually come back here and from other import func, this is going to fail. You see, can't import do stuff. Maybe well, why yes, because the do stuff object has not been created. But why hasn't it been created? Let's try to import stuff, the module stuff. It also doesn't allow us to create anything because of the exact same reason that we have this circular problem, circular import problem. You see, now it works. So this is something to look out. Python actually raises exceptions when it detects, well, it tells you when it detects a circular import. So well, let me read the chat. How is the absence of explicit import could be a good idea? It is very annoying to always import every sub-package I need. I would dare you to write code that does not import anything and make it look maintainable. really. So you put everything, every package, you actually copy paste NumPy code into your single file, and you start bloating and bloating and bloating. So this is one absurd point. Another point, yes, it is somewhat not very intuitive when you use relative imports, but that is just well, you're actually crawling around the directory of your own project. So make your project, organize your project in a more clear and transparent way. So that's my reply to this. In SciPy you do, okay, in SciPy, maybe this is a good example of, let's have a look at SciPy. Let's inspect what goes on there. github.com/SciPy. SciPy, this one, okay. It is really annoying, I agree with you. Now let's have a look why it might be annoying. For example, it has dunder init here. Okay, it imports some stuff, which is very complicated, and it sees if the import is not within install, not during install process, stuff like this. So really complicated init, maybe due to legacy reasons. And for example, we have to import FFT. FFT does some stuff. Maybe you can provide an example of how, which lines exactly, but I can't really see why it could be the reason, outside from the fact that maybe this dunder init here just does not export them. If, for example, I do something like this, like you see, I have this situation here, this one. Let's emulate what SciPy could presumably do, so, which makes everything annoying. Let's mkdir, please, okay, project, and let's call it FFT. Doesn't matter. And inside FFT, let's put a proper stuff in there. FFT. First of all, put dunder init. Py, yes, and then we put some fft.py, don't care. We see that we have created something here. Do def fft, whatever, print fft. We have implemented Fourier transform, great. Now let's actually be nice and expose this fft, that we created, from this sub package. We do import .fft, sorry, from, I always mix up, import fft, okay, it should work. Now let's have a look at the source of your frustration. I have just created the source of your frustration anyway, so let's have a look. Can we import do stuff? Yes, we can. Can we import okay, let's try it another way. Sorry, come on. In Python, import proj as SciPy. You see, SciPy now has only two stuff, and it does not have FFT. Why is that? Because I did not explicitly instruct dunder init to expose it. And at right now, this sub package FFT is just exists there. It is not. It is in no way declared, not declared, but in no way importable in this manner from SciPy, because you see has no attribute FFT. And how do you solve this in your actual code? Well, you do import proj FFT, and now you see that your proj.fft has FFT. sorry, FFT. You see, the problem here is that SciPy in its root dunder init, like we have this one here, this one, not this one, but this one. This dunder init exposes functionality from stuff to the outside world. However, it does not expose FFT from the outside world. There might be a sort of resource reason for this. Suppose you write some complicated simulation environment, and it takes a lot of time to load. So suppose we, in this current case, we wrote this simulation environment within our FFT, and we do this: import from .fft, from .import FFT. Suppose we do this, and suppose FFT takes enormous times to load. Let's simulate this. Import time and time sleep 10. Okay, let's have a look at what this does. Python import proj. I have exposed FFT in the core dunder init, so it is visible. And let's just import it. Proj FFT. It still has no attribute. Oh, I haven't saved it. I'm sorry, I haven't saved it. Let's import it. Right now you will see what I'm talking about. You see, we are waiting now for 10 seconds because I instructed it to wait for 10 seconds here before it loads. This might be the reason why sometimes you do not expose your functionality in the core dunder init, and you require the user to actually populate and let's say make your code ugly with all those sub-package imports. This might be, I think, the best explanation of why SciPy did not do as well, did not expose it directly as I just did using this. Because right now we have to wait for 10 seconds. So this might be the main reason. So this has got nothing to do with relative imports or anything. It's just maybe some decision that they made. For example, if you write some complex software that uses some actual hardware to do computations or do simulations, your actual hardware actually needs some startup time. So but in many situations, your users don't need that hardware. They can use actually a model of that hardware, which takes nanoseconds to load. So that way you can both ship this functionality inside your single package because it is related, and it is related to a solution of a single problem that your users need. But you don't actually ask your users to wait for half an hour each time they want to import stuff. For example, if we for instance, we can take Torch. Torch requires some time to set up device contexts when you have GPUs. But the whole point of Torch is to use GPUs. So they actually decided to set up context upon the very first import of Torch in any code. So that is why you have to wait. You have to wait not too long, but still this step is necessary. It might be like 1 second of wait on some especially slow systems. But anyway, so this is the whole problem, source of your frustration with SciPy. They decided not to export it, not to expose their functionality, and just instruct you to populate your own workspace with the stuff you need. So that is the main reason. Now, let's get back to our package structure. Well, and luckily we are just discussing import visible objects. So essentially, if we have a dunder init file, it can instruct import Python's import machinery to make some functionality visible, some object visible, or some stuff. For example, PyGym makes visible the environment and the environment, yes. And when you init a certain particular game, or you initially import some simulation, it exposes its other stuff, certain instances of that environment. So here we can see that package foo is, well, if we just do, we have these two files, like I showed you in the physical example here. This here allows package.foo to be visible when you just import it like this here. Now, unfortunately, this thing does not. If you don't include bar there, you won't be able to see it, and you'll have to call that scipy spaghetti import. And the same holds for buzz here, because buzz is not imported upon the import of the whole package. Because you see, like import, Python's import. First, look at the structure of the package. It understands that it has some packages, subpackages, and modules, whatever. Then it looks for import, and then it executes. Then it looks for the file called dunder_init. It executes that file and populates the namespace of the package with the result of the dunder_init plus the subpackage plus let's call it entry points to subpackages. Of course, dunder_init can override those entry points, but in any case, upon import of this thing, it executes this and makes this thing accessible when it has been dealt with properly in import. These things are not accessible, but they are visible by import. So you need to do this this code. Now, moving on. It is well, in the previous session you discussed some ideas of how to do abstractions to make your code logically cleaner, so that your business logic is not hidden behind some very obscure patterns or very obscure coding practices. So the same applies to package organization. It is always nice to first of all put related things closer together and unrelated things farther apart. Yes, it's first thing. And secondly, it is important, since the close things are put together, it is important to it is nice to have a proper name for for these things. So, for example, if we have a project structure like this, yes, and we have not seen the code. Right from the get-go, we can understand that in the pipeline.py, of course, we need to have some domain knowledge, but right from the get-go, we understand that pipeline.py realizes some, maybe it's plumbing, but since we also see a model and attention and the config, we realize that that's sort of data processing pipeline, not a plumbing pipeline. Then we see a folder core, and we sort of understand, yeah, there's something important there. And we see we have load, which loads something, and the model, which models something. And in model, we have ATTN and LSTM. LSTM allows us to, for example, figure out that there is some recurrent neural network there. And given that, ATTN, in the context of LSTM, allows us to understand that there are some attention models inside. What I'm trying to show you is demonstrating is that naming your project.py is a bad name. It's an all right name for your package, although it should be better, but it is a bad name for submodules. So submodules names of submodules should reflect their core their responsibility. So this means that attention here is responsible for attention models. LSTM responsible for new recurrent models. Maybe I should have called it RNN. I don't know. LSTM, possibly LSTM models. Models means model here means that this subpackage realizes models that you can use for what you can use in experimentation. Load maybe realizes either data loading or model loading. We don't know yet, but anyway, it is clear what things do. And finally, pipeline possibly realizes some let's say choreography with loading and modeling and using configs. As you can see, this is like it's a generally good idea to step aside and think about how to name your contents properly. So to recap, if we implement it in a single module, it's going to be a mess. It will be hard to maintain, but easier to distribute though, but hard to maintain. And if you have a break for a couple of months from your project and then you get back to it, you will have a really bad time and a lot of frustration with it. So let's move on to what you might probably think as another reason to use single standalone .py modules is that you can actually do stuff like this. You can run them as scripts for data processing. There are a lot of code out there that perform some data science or machine learning computations, neural networks, like this, and they just ask you, well, come on, type Python, train, and a crap load of arguments, and it works. Well, yes, it works because, first of all, they wrote a script that serves only as the gateway that parses arguments and runs the computation which it imports from a project or from elsewhere. But Alexander, I don't really know why you want to avoid relative imports this much. Could you please provide maybe some, I don't know, a link to a discussion where, okay, if you the key is, of course, you can have them imported, and I can actually show you right now. No, I can't show you that because that's the whole point of today's presentation. Not only just models, but also setup scripts. In order for your project to be installed, you need a setup script. Okay, you write a setup script. We will get to this in a couple of minutes. And then what you do, you need to install it. You install it, and then there is a question of how you install this project. If you are developing it, then you can install it in development mode, and your changes will be reflected in Python and will be visible from anywhere. And this way you can actually use absolute imports. But what if your name of the project changes? What if after some consideration you decide to name your project? So you have to, in all this project, in all your modules, you have to replace this gem with not gem but OpenAI gem. This is not of course it can be easily made, or maybe sometimes not so easily, but why do you need this work when you can just we could have used relative imports and did not even bother with naming or renaming stuff. So that is one. So of course you can, but why make your life harder when you can make it easier and clearer? So anyway, you can run scripts, standalone modules as scripts. The general recipe for this is you have some function, you have a special scope, if main, let's call it if main, and inside you parse the arguments and it works. And then you take the arguments and pass them to the function, it works. However, you might say, if I have a package, can I do this? Yes, you can. You create a special file called dunder main, and it does the same thing as you did here, except you need to import your functionality. This way, you sort of package inside. This is not a word. This way, you ship the ability of your package to be run as script when you distribute it, and inside the package itself, not as a separate standalone script, which might clutter space or interfere with existing modules that Python has in its side packages. That's the folder where the directory where it keeps everything. So this is a nice solution. It works with sub packages too. For example, you have a dunder main in your core package. For example, you have a dunder main here, and you have a dunder main here. If it makes sense to also be able to run mtfusion.core as a module. So let's have a look at a particular example. This one is here. CD FDS seminar packaging if main subl. Let's have a look at Sublime. What it gives us. We can close this thing. It's about strategy pattern. To be honest, I don't remember. Don't have this, like, I can't map the name into. Could you elaborate maybe some core principles of that pattern? I just don't remember what it means. Anyway, we have experiment here. We have main here, and we have experiment here. Now, this is example. Yes, example 9. You see, up until recently, you could not do relative imports from dunder main, and you had to do absolute imports from here. But actually, quite a while ago, there was a modification to PEP, and which allowed the relative imports in dunder main, which means that before, I guess, Python, which Python is? It's actually quite an old one. Before Python 2.0, you should have done something like this. Yeah, if it exposes. But right now you can just do it like this. And it works with the stuff you expose in dunder init and or sub packages. So anyway, we have here an experiment. Yes, this is the experiment that I took, just copied from here. It takes something and it should work. Let's try. CD, no, Python, experiment, example, experiment. Yes, and it swears at me. It requires some arguments. Okay, 1, 2. You see, it prints 1, 2. Okay, 1A. Prints 1A. Great, it works. Nothing's broken. Now, before we install this, yeah. Well, sorry. No, it works. Now let's try to run this same thing as using not experiment.py, but the dunder main. We have to specify the -m flag and let's see if it works. You see, it also, maybe wider. You see, it also did the same thing. However, right now, I'm not running my standalone script as a script, yes, the whole model as a script. I run the whole package as a script, and the logic of the package being run as a script is entirely specified in dunder main file. So you see, of course, I separated one functionality from another functionality. Here, for example, in the original file, I could actually import from the package itself, but I also had this clunky looking namespace which precluded this thing from being run on import. This thing protects this piece of code from being executed on import. Of course, I could have just removed it and made in imports, but well, that's up to you. For example, I found this thing to be more, I don't know, cleaner. I don't have to specify the whole path to this file, and just -m makes it shorter. Anyway, you can always write the code in dunder main to make your package run as a script. Now, here is the main the main message of today's the main part of today's lecture. Then we'll try to work on some old code of mine. So a package distribution. So in order to make a distribution, you need to collect your package and relevant resources for the package into a single file that can be downloaded, yes, and installed in using some other script. For example, installed from Pipey, or installed for using your Docker manifest. So when developing your project into a package, you need to organize your package. But when developing your package into a distribution, you need to first of all only write a setup script, and that's it. So a simpler goal. However, when writing a setup script, you will realize that you sort of need to move back and forth in terms of how to properly organize your project. There are many different variants of how to reference sources of your project from a setup script. I will focus mostly on the most transparent and straightforward one, which I tried to experiment with many ways of organizing code, source code of the project, and I found this one to be more to be clearer. And this is one of the most this is the most popular way of doing this in other packages like scikit and stuff like this. So in order to write a simple setup script, we first need to make sure that you have setup tools installed. However, nowadays setup tools is sort of a part of a standard library. Of course, you can find. Of course, you can just download Python from python.org. It won't have setup tools. It will only have its predecessor distutils. But distutils had many limitations, which setup tools actually improved and overcome. So only in very rare cases you have to run this line in Conda, which I advise you to use because it's just easily distributable. In Conda, this is if you create a separate environment, this thing is there, so no problem here. Because, for example, because in some ways pip requires it, and in other not requires but recommends it, and in other ways NumPy and other packages use its functionality regarding compiled extensions. I will get to them in a minute, a bit later. So setup tools is just a package which provides you with a set of objects and options. But the most important to you, in order to be able to make your package into distribution and even upload it to Pipey, is import setup extension and extension. This thing is necessary for you if you have some C++ code and you want to actually interface C++ code to compile it. The interface is up to you to write. But this is the corest of the core that you need when you write a setup script. As I mentioned, there is a predecessor distutils, which has many limitations. And in fact, Python's official documentation sort of links to setup tools documentation in many aspects, directly links. So they sort of understand that setup tools now is sort of a standard for packaging in Python. And finally, if you are very keen on Fortran code, for example, you use some old scientific libraries, or you use, I don't know, some heat equation modeling, which was written mostly in Fortran, you actually need to first import setup tools. That's very important, and NumPy actually instructs it to, but then import from NumPy. This way, the functionality of all setups and extensions here are built one on another. But for example, NumPy's extension allows you to compile Fortran code and C code and Python code. But setup works everywhere the same. Now, so the minimal setup script for your project is this one. If you properly organize your package, yeah, and put dunder init in every subdirectory, this script will solve most of your problems, because it uses it will solve most of your problems. And let me explain you why. The first argument to set up is the name of your distribution. For example, in scikit, it would be scikit-learn, not sklearn. The second line is the version of your project. Since your project is in early stages, you typically put 0.1, which means that it's extremely experimental, no API is stable, please use at your own risk. And the final line is actually the line that declares which sources are relevant to this distribution. And here it uses a function called find packages. Let's see what it does here. For example, I have this example if main, yes, and let's see what find packages does. I Python, and we import, and let's see, we are at the root. Okay, let's call find packages. Find packages, and let's call it with a dot here. It finds an example. Okay, great, it found an example, because it actually scans all directories in this path and subdirectories, and if it has a dunder in it, then it includes them. Otherwise, it leaves it out. Let's try the same thing with scikit. cd github scikit and IPython, and let's call the same thing. Find packages here. Quite a lot of them. You see, it moved around through the directory tree and inspected the dunder needs and found the subpackage that resides there. In SciPy, it would also do this, but as we have discussed, SciPy for a reason does not export, does not make its subpackages visible when you import. However, this function will still detect them, because every subdirectory of SciPy in SciPy package has a dunder init file. Now we can actually try to verify if this claim is actually true. So fds packaging main. Let's try to remove. Okay, let's try to remove this file. Delete file. Okay, let's see if it works. I hope it won't work. Anyway, you see, it didn't work. It didn't find the dunder init file, so sort of everything isn't very good. Now let's return stuff. Git reset hard head. You see, like git reset with hard, put everything back in its place. Anyway, in some cases, Python requires different versions of GCC. For example, in Linux, it's okay to debug this, but in Windows, it requires Visual Studio and DLL files. How to handle this step? Or is it better to print an exception and that's all? We will get to extensions in a couple in the second part, maybe within 15 minutes. But the general idea is that you need to first of all specify the paths of the DLL of the shared objects in Windows and include files. And make sure that the user has them installed. Now, the thing is that if you want to build your project on Windows and distribute it, then you should actually, in Windows, it is recommended to distribute not source distributions, which need to be compiled, but binary distributions, which have everything already pre-compiled and which have a look, which look into the lookup table of dynamic link libraries and pull the resources from there. So in Windows, if you want to, well, if you're a developer and you understand what you're doing, yeah, and you want to share your library with another Windows user who is not so great at developing, but who needs to use it, you should actually distribute a binary distribution. We will get to that, in a while. But in Linux or Nix systems, of course, it is possible, and it's sometimes recommended to have binary distributions because libraries, hardware may change, libraries may change, stuff like this, and maybe some flavors of, maybe for example, if you have a GCC compiler that is not CLang, but which is more advanced in that it supports OpenMP, parallel code style, then you can actually build your software using a GCC that has this OpenMP, not Clang, yeah, and then distribute it to into an environment where there is no GCC at all, and it will still work. But if you do a source distribution, then you have to actually compile it in that environment, and it's going to be a headache for you. Now, as I've said, you need, these are three important arguments in setup function: name, version, and packages. Packages is the content, version is the identifier, and name is the name of the distribution. You can't have it unnamed because it's silly. Usually the name of the distribution in, let's say, in homebrew projects, usually the name of the distribution coincides with the name of the package that is being distributed. However, scikit actually uses scikit-learn, whereas the package is sklearn. So they're different, but that's all right. It won't interfere. The key issue here is whether it would interfere with some existing or some other library which is absolutely unrelated to what you're doing. So come up with a better name is all right. Now, a secondary use of the name here and version here is for piping. If, for example, if you want to publish your don't care. If you want to publish your code in package index, you need to actually have a little bit more than I have just more than this setup script. It should include your name, your license, your description, keywords, and more meta information. I'll get back to this. But anyway, on the package index, your project, your distribution of your project will be identified by the name here. And the version keeps track of whether anything changes or not. I won't get into much detail about versions, setting a version, but the core idea is that 0 here indicates indicates that your project is experimental and no guarantees to the user regarding the API and the exact binary, let's say, compatibility in terms of different subversions of your project. The second number means that this is like a version with some extra functionality, and an optional third number here, which is not present here, is maybe a patch, a fix, and stuff like this. When your project is version 0, like this, it doesn't really make sense to have patches. You can do all your improvements in minor versions. However, when your project reaches some sort of maturity and you feel that, yes, this well, if you're developing a library, of course, it's not very relevant to scientific code, but anyway, when it reaches maturity and you feel like it's ready for version 1, then you indicate it by changing the version. But this also constrains you in that you can't actually change your API willy-nilly, and you have to go through deprecation cycles, of course, provided you have a user base. If you don't have any users, then nobody will care, nobody will notice. But if you have some users, and so maybe your colleague is your user, or your older code or your code elsewhere that runs on a cluster is also a user, although these users, some of them don't have, are not represented by a physical human being, but still they are also users. So if some changes take place, and that code would fail if you just change its API. Now, let's, we have 10 minutes before we can try to discuss for example, if you feel not convinced that making packages out of modules is a good idea, or, for example, your functionality that you want to export is so small, so tiny that it fits within 164 lines of code, 640 lines of code, then, well, that's an arbitrary number. Then you might think, well, there's no real reason for me to make this directory structure. How can I ship a single module? Just does this. This module takes your URL lib, for example, takes some interfaces with the shell, or does very simple stuff, but it's a single package, that single functionality that does not need to be cut and pasted everywhere else. Okay, you can instruct your setup script to ship the listed modules as standalone modules. For this, you use not packages, but py underscore modules, and list the files that you want to ship. However, don't forget that this tiny.py, well, it is not the same as tiny project. Yes, you see this. Your modules will be importable by your code from anywhere else after installation under the name tiny. Okay, so you have to choose wisely the name of the module. So let's have a look at how it is in fact how it looks like. We have here setup script, the simplest of them all. 9 lines. I use setup, example version, and py modules. I don't need to specify py here, but so, and this thing actually does some well, this functionality. It does something. Let's have a look at how can this be installed. For example, you have prepared your code and your setup script is ready. What you do? You say, okay, pip install. For example, your for example, we just want to install from this directory within which we currently work. We can use a dot. Pip is smart enough to figure out that you want this folder directory to be scanned, the current directory to be scanned for setup, and follow instructions there. You see, if I hit enter, it will going to do something. Look, it created. In fact, it actually performed a little bit more than necessary, but essentially it created a distribution, yes, called wheel, and then it it built it, because sometimes it needs building, but in this particular case there is nothing to build. Everything is there, and then it installed it as example 1. Now let's try to change the directory here. For example, this is my home directory, IPython, and first of all, let's try to import example 1 here directly. Port. It won't work because the problem here is that my distribution name is not the same as my package name or module name, because my module name is tiny and the distribution name is example. So what should I do? I should import tiny, and it works. Now let's see if it really does the things that we actually want it to do. Let's call it full, 1, 2, and none. 3 arguments, but 3 were given. Okay, why does it do this? Because it takes positional arguments, but it takes keyword arguments, but I use positional arguments. Okay, so this is my bad. Anyway, it works. You see, this code takes keyword arguments and prints them. Essentially, we have installed our package. The main takeaway here is that the name of the distribution is not the same as the name of the module, and sometimes it may get confusing, especially in the case when you just want to set up to distribute one single file somewhere. Now, here is an example. We have 5 minutes. We can make a break a little bit early if you feel bored or tired. So it's up to you. No one? Okay, let's have a break then until 5 minutes past 2. Yeah, I hope 10 minutes is all right. All right, we are about to start, so within a couple of seconds. Fortunately, my Zoom experienced some problems and had to be restarted. Okay, so let's. It looks. Okay, maybe it looks better. Is everyone here? We're ready?
Yes.
Okay, great. So let's move on then. So we have just covered how to distribute your standalone module, which should, by its in principle, contain only some basic core functionality without any other whistles and bells that add to its richness of user experience. Okay, so let's discuss how to distribute packages. I have shown you how find packages function work. It will suit most of your needs. However, I feel certain, I don't know, joy when I specify the list of packages myself, like here, for example. So for all your cases, this thing will help you and will do your work, provided you put dunder init files in everywhere it is necessary. Everywhere it detects the package structure through those files. So if for some reason I do not recommend this package structure as it is, this package structure, but it is sometimes used in more engineering environments. For example, you have the root of your package, the folder where you sort of develop, where the setup script lives, and you have src directory where contains some core functionality. It sort of, it's not a rule, but it's a rule of thumb that in src files inside them there is something that needs to be compiled, like a C extension or Python, maybe even CUDA kernel lives there. It's sort of like a hint to the reader of your code, to anyone who reads your code, that might be somewhere something that needs compiling. However, it's not necessary. It's just a hint. Now, for example, in src directory, you have some core functionality, some core modules, and in project you have some experiments, some data loading stuff, and stuff like this. So in order for this structure to work and to be understood by your setup script, you need to, first of all, you need to think really hard whether it's necessary to put core functionality outside of your project. Okay, but after having made the decision, you need to specify, to instruct setup to look for the core part of your project in a special directory. This is done through package _dir dictionary, which maps the name of your package or sub package. In this case, it is sub package, to the folder, to the directory relative to the root, or to where the setup script lives, to the directory of the source, for the source of that particular package or sub package. In this particular case, I instruct setup to look for the sources of project.core submodule, sub package in src. However, the rest of the project, as you can see, is in project directory. The rest of the project will be setup will not have to look anywhere else, but in the default location, which is the name of the directory, which coincides with the name of the directory where the sources live. So this package will look here, and this package will look here because I instructed setup to do so. The main problem with this way of organizing your package is that if you install it in development mode, I will talk about this in a minute, what it means. Essentially, it means that you instruct pip to make soft, to essentially to put a symbolic link in the Python library, in the directory of Python libraries, of Python modules that you use, the symbolic link which links to the root of your project. So essentially, any change, any update you make locally within your work environment is immediately reflected to globally and immediately visible from all locations of your system. So, for example, if you are enhancing scikit or developing your library, it is recommended to install it in edit mode. However, when you want to deploy it on a remote machine, on a cluster, actually installing it with editable installation is a bad idea because there is nothing to edit. You just instruct pip to take a zip file or a tar.gz file. In this case, if you have project structure like this, it will be very hard for you to work in editable mode. You have to install your project, and this way your changes will not be reflected, and you will have, in order to update them, you have to reinstall your project. This is annoying. So I do not recommend using this particular structure where you have a dedicated folder for sources, unless it is really, really important or dictated by either your legacy software that you use or legacy shared objects that you need. But well, if nothing else dictates you to do this, then don't do this. Just put src here inside the submodule core of the project. So essentially, do something like this. This will be much better and clearer for you later on when you use this stuff. So you just put core here and that's it. This will work and will suit most of your needs, and will be will give you much less headache. So this is much better structure, this one. But anyway, well, we can have a look at the particular example, which is some packaging, and this is not, what's this? This is charming surf. Oh, let's do this one, and we'll have a look at here. Here we can see this replicated structure. It is installable, but as I said, it will be hard for you to. It will be not inconvenient for you to develop it. You'll have to reinstall it. This is how it looks like. It's an empty project. Next, what we have? What other options we have? Well, it is not uncommon for your code to rely on C or C++ code, because you can't argue with that, with the fact that C++, well-written C++ code is order of magnitude faster than Python. And the whole, maybe, how to say this? The whole idea of Python is to actually be a conductor with respect to an orchestra, where each individual member of the orchestra is some high-performing, low-level written module, and Python just orchestrates the interaction with these modules and hides the really, let's say, hides the machinery, the pure computational hardcore machinery behind the scenes, and exposes the logic of what your project should do. of what your code should actually accomplish, of which transformations it actually, and in which order the transformations are applied. So it sort of separates backend from front end in some way. So it is not uncommon to have extensions, as I said. This is done using, yes, I have an extension. Yes, let's call it, sorry, this thing here. This is done using the extension object from setup tools. This object is essentially requires you to name the module by under which this module will be importable by your project or package, sorry, by your package. List the sources or the source code of that particular module, compiled module. List the libraries it needs to link against when linking, and include dirs to actually specify the include directories. So if you have seen C++ or C code even once in life, you sort of remember what include does. It allows you to, it's essentially like Python's import, but more, let's say, more brute force, let's call it this, yes, but more brute. And it has other options which are linked here, but I'm not going to discuss them right now. These options include maybe some, first of all, compile flags, and also maybe, I don't know, some special directories to locate shared objects. The same holds for DLLs in Windows and for shared objects in Unix-based systems. However, in order for your code to be distributed to a machine that is not yours, and that machine happens to be Unix-based and your machine Unix-based, then you should binary distribute. For otherwise, in source distribution, you have to compile it on other machines, and as I have said in the first session, it is not always possible because the user might not be very technically inclined in that respect. So, if you have Cython, for example, Cython, to briefly, is a variant of Python, as actually a sub-language of Python, which is strictly, which allows strict types, because Python is duck typed. For example, if something behaves like an integer and can be added, then it's probably an integer. If it walks like a duck, walks like a duck, and smells like a duck, it is a duck for all intents and purposes. This is the idea. So, however, Cython is sort of a language that allows you to write Python code, very, very Python-like code, by which I mean it is looks like Python, it computes like Python. However, the only restriction is that it needs to observe the types and type transformations like C does. But then what happens is Cython takes this code and it converts this code into a pure C++ or C code, which can be used as that is later can be used for compilation and linking, and finally produce you the module that you can later reuse in your package or in your distribution. Now let's have a look at how this is done. You need, first of all, to have Cython installed, yes, and you need to actually import. Well, if you do not use NumPy, if you don't use let's say extensions of setup tools provided by NumPy, then you actually by default you do you do the following. You take a Cythonize function from Cython, and inside your setup you specify extension modules, and you just wrap around the list of your extensions inside the Cythonize function. It will automatically understand if an extension is a Cython extension or if it is a C extension. If it is a C extension, then it has no effect. But if it's a Cython extension, then Cython will run and interpret your code from Cython language to C language, and then repackage it as an extension and will let setup do its work. How it looks like in a real package, not on a presentation. You see? I can't zoom here, but you see, here is a wrong file, and this is the right file. I tried to be very verbose here and include lots of interesting stuff. This is most of you won't need this because there are many ready libraries for you to use. However, sometimes in certain applications like well, some of my colleagues from 3D, from computer vision division of our group, they had to write some code in C in order to allow them to implement an algorithm or for faster processing. So when we provided an example with bad structure, did not get whether it will be a problem in that case or not. In editable mode, it will be a problem because you won't be able to access editable mode. Basically, links makes a symbolic link to your root, to the root of your package where you develop, and that's it. That is, and also adds some meta information. So it will be a problem there. However, if you just package it properly, for example, without the src subdirectory and just put core inside the project, it will work fine. So that's the only problem with that that setup. As for Cython, for example, if you have compiled extensions and one of them is Cython, another is C, and third one is Fortran, for example, if you like this, then if you make some changes in the code of one of each extensions, you'll have to recompile your project in order for these updates to be reflected. However, if you are in development mode, you don't need to reinstall this. It's only recompile. There is a special, I will discuss this. There is a command you can use to recompile your extension. For example, I will show it you right now. CD, let's conda activate Y38 because it has better compilers. And let's CD into our extension. What do we have here? Extension, yes. LS. And we have a lot of stuff here. In order for this, if you, for example, let's first of all briefly have a look at what we have in this package, shall we? We have src file here, folder, which contains primes. This function is a very silly function. It just gives you a list of primes, that's it. And inside we have a file, C file called module.c, which lives in a Python subdirectory. Usually this hints to the developer that this structure, src Python and module, indicates that probably this file contains interface from C to Python, direct interface. This is really that's not so hardcore, but this is I hope that you will never encounter the need to write a direct interface from C to Python. However, the example is here. This code, C code, simple C code, it first of all it uses include primes.h, which resides in include here, yes. And secondly, it is adapter, but adapter is a richer pattern. For example, I will discuss it after this thing. It is an adapter, but this is mostly interface because you can't use C code directly in Python. Adapter is something that makes your code, older code, or code that is that has a certain specific use and use pipeline, be compatible with Python patterns and Python, let's say, code semantics. For example, if you have a database connection, yes, database object, you need to connect the database, and then after you have done stuff in the database, you need to disconnect from the database. Obviously, you can just take import dbcon, yes, and then dbcon connect, and then do some SQL queries, dbcon disconnect. It is all right. This code works. However, you can adapt this code to better reflect Python code patterns. The pattern I'm talking about here is this one with dbcon as con, and you put code here. This thing will automatically, first of all, handle exceptions for you, by which I mean if an exception here takes place that requires you, that either requires you to abort stuff or to kill an application, this pattern, this actual Python construct with allows you to disconnect from the database as soon as anything bad happens. But if nothing bad happens, and for example you successfully go past this scope here and end up here, the connection will also be closed, because with specify is a special construct that specifies the so-called enter and exit operations. An enter operation here would be to create the dbcon object and name it con and make it available in this scope. The exit operation here is to disconnect, and this will automatically disconnect. So in order for your DB connection to be friendly with this clear and simple Python construct, you will have to write an adapter class, and an adapter by which I mean you have to specify the dunder enter and dunder exit methods for dbcon in order for it to work like this. So this is mostly one use case of adapter. I won't go into more details. Another use case is, for example, if you have a list of rows and you actually make it so that it is iterable using an ordinary Python for loop. It's another adapter. So adapter basically adapts your code from older version or older, let's say, pipeline to a new, more clearer pipeline. Anyway, here is mostly interface. So this code essentially this creates the function that can be used in Python. You see it uses PyObject and PyObject here. This construct, just believe me, this construct declares, first of all, this one declares the list of functions that this C module exports. And this construct is a declaration of the C module itself. Here is the low-level initialization of this module. You see, in C, it looks quite hard to understand. Now, let's have a look at what this thing looks in Python. We have fastprimes.pyx. Look how everything here that was written in C looks in Python. You can even see parts of Python in this code. This is Pythonic, and this is Pythonic even. Maybe this construct for else is not very familiar for you, but still it is Pythonic. For else means that if you did not break from the loop, then you should execute this piece of code. If you broke from the loop, then this piece of code is not executed. Okay, so this is how it's written in Python. And I won't show you the timings, but we will see that this code works on the same speed as pure C code. And finally, we have the implementation of the same function in primes.py. Very simple and clear. Now, how all these three different versions of the same functionality can be set up using setup script. First of all, I call Sysonize on the list of extensions. You see, this is the list, and I call Sysonize. The first extension is Syson extension. Sysonize will convert this thing into a C file, and then make it so that setup would understand to compile that file under correct name. This second extension instructs, Syson will ignore it because everything is in C here. So Sysonize ignores this, but still, well, it ignores by means that it does not affect anything there. So this instructs setup that under example.cpp subpackage, there must be a compiled extension built from files in src directory, and that's it. It also specifies which default include directories should be used. And also, as I have mentioned earlier, it specifies some optional arguments like compile arguments. There are also linking arguments and the language flavor. Here I instructed it to use C++ flavor, even though the files indicate that it is a C file. Now let's have a look at how this actually builds and what it does. First of all, I will simply try to show you how to build this thing. The command, this one, this command, yes. It runs setup as a script and instructs it to build extensions. I think you see why. Let's press enter here. You see, it spewed a lot of debug information into the console, quite a lot of it. And let's have a look at what actually changed here. First of all, in our folder, we see fastprimes.c. Let's have a look at what this is. I tell you that this is the translation of Syson file into C. This is a huge file. 3,000 lines of code in order to implement this thing. And inside this file, there is declaration of module. There is, you see, these are the what metadata Syson used in order to construct this file. So inside this, you have declaration of modules. It's really hard to understand this file. This file does not need to be, for example, if you want to push to a remote repository or to save the file, you don't need to do this. This file is automatically generated and will always be written by the next call to build your project. So this file does not need to be committed at all. You can ignore it. The only important file is pyx file. Now let's have a look at what we have. Let's find where our build extensions sit. They don't sit in src, neither do they sit in project. Where do they sit? They sit in this folder called build, this one. Inside we have a subfolder specifying the operating system, its version, and its architecture, and Python version. 10.9, x64, 86, and 3.8 Python. Inside we have example, which is empty. I don't know why. And here we have a temp folder. A temp folder also is empty. Why is empty? Because I do not see it through Sublime. Let's open the folder using standard finder. Okay, let's have a look at what we have here. Build, example. You see, we have now these CPP, CPython, and PyX, CPython. Let's compare with the setup script. With setup script, you see that example 8cpp is here, example CPP, and example PyX is also here. So essentially, it built our extensions. However, they are not usable right now. These are the object files for the build process. Anyway, these are not usable right now. How do we make them usable? Okay, let's pip install it in editable mode. You see, it did some magic, and right now nothing has changed here. I have this same shared objects because I wanted to show you how you can write code in example in C with C interface and Python, so that there is no so you won't be confused whether if it's applicable to one case or the other. It is applicable. So now let's have a look at how this works. I'm going to intentionally cd to home directory and use IPython. So our package is called example8. Let's have a look at what it does. Import example8. Example8, yes, what it offers us? It offers us CPP, Py, and PyX functions, yes. And at the same time, it also offers us a test function. Let's see if it makes sense to us. .init. Okay, so in my init file, dunder init file for the project, I import from the compiled extension .pyx. I called it this way. You don't have to call it this way. I just call it so that it indicates that it was built from Python. And also I import this the same function primes from C extension compiled from C. However, I assign them special aliases so that they will be easier to use. And of course, from pure Python module primes.py, I import the prime function as well. So you can see I can, first of all, let's ask for 10 for 100 prime numbers using Python function. You see, it's not very, let's ask 20, so it's smaller. Yes, you see prime numbers. This code returns prime numbers. The same code, but with Python Python extension. It also works. So essentially, because I built it so that it works. In Python, it is really easy. In C, it's not so easy, but it still works because there was some effort put into this. It works. Now let's see, well, I have written a test function here, which essentially takes Python function and compares it against Python and CPP built extensions. And I limit the number of primes to output to 10,000 so that because I don't have to deal with dynamic memory location, stuff like this. Now, example.test, and let's write 9999. It works. So basically, it passes the test. Now, what about the speed? Pi, and I'll put a semicolon there so that it won't print stuff. It takes some time, about 3 seconds. If I use Python, it is immediate. If I use CPP, it's even a bit faster. So the question right now that has been raised in chat, why do won't this thing confuse Python? Do I have I have now folders CPP and compiled extension CPP? What's going on here? In dunder init file of your project, you can, in fact, you see, by default, before the dunder init file is executed by Python import, at this point in the execution process, by default, nothing is visible to the user when the user imports. However, after this line, import dunder init makes visible the function primes under the name py to the user. Here, on this line, Python import machinery understands that I want to use here. It understands that this is a specification of the location of import, i.e. the package and sub-package. And this, it understands that this means that I need to import from that sub package. I need to import from that sub package function primes and call it pi(x). This line altogether makes the function primes from Python module visible to the user under this name. Same goes for CPP. Even though there are no such folders, the thing is that there's not necessarily the Python does not always, as you remember, there must be a module or a package in order for Python to import from there. So Python, in this particular instance, imports from the compiled extension, which is a module, a compiled module. So this is how it works. So although there are no folders, these particular files, although they do not sit in here, but they are very carefully linked to by pip upon installation, they are accessible. So maybe we can have a look, or do we have time? No, we don't. Okay, so anyway, these are compiled modules. And you cannot actually compile a package. You can compile a module, and the package contains compiled modules and pure modules, Python modules, and that's it. A compiled package is something it cannot exist, because the package is a sort of like a directory of modules, some of which are Python, some of which are C. Now, anyway, so this is this script essentially, which I showed you. This one. This here is how you link CIF extensions or Python extensions to your Python package and work with them. Next, for example, yes, we have discussed a lot the questions of developing in editable mode. You have to recompile your extensions if you change them. That's obvious, because binary code does not reflect any change in the source when a source is changed. You need to compile it. So there are. So let's move on to the types of distribution finally. So we have prepared the setup script. We have prepared the structure for our project, for our package, and we declared all the extensions that are needed here. So here, let me do this thing, and cd GitHub, yes, same packaging and extension. Okay, so clear. Right now, there are two distributions. Source distribution, as I said, it takes all the relevant files, sources of the package that you declare in setup. It collects them into a tar file or target file or zip file, and it just gives you, and that's it. That all that source distribution does. Source distribution is created from just if you call Python setup, but specify here as dist. This is a terminology, because if you will be talking with other Python developers, they will, if you say as dist, they will understand that it is source distribution, not something compiled of two words. You see, it did some, well, the output is here, running as dist. It creates some information, meta information for the distribution. Then it runs check. Check step helps you identify missing meta information. For example, here it says, well, metadata is missing. Also, author and author email is missing because I have not supplied them. And then it creates the necessary structure, moves, does, then you see it copies files, README, setup, then meta information about these, the content of the package, the source distribution. Then it copies the PY files, C files, and creates the archive, and that's it. How it looks like in reality. you see here we have, I will close this. Build is not a concern for us, and we have dist folder here. You see, in dist folder we have example 8.1. Let's have a look at what is this in what sits inside this example. I will open this and let's have a look. Let's compare. So we have this thing here. Do we have it here? Yes, we have src here. You see, this thing is from here. So essentially it copied everything. It copied your structure, your project, your code. Unfortunately, it also copied Python code, because it is because for this fine control over what gets copied or what gets eliminated, you need to specify something called manifest, but it's easier for you to just clean up after building extensions and be done with it. It is beyond the scope of today's seminar specification of manifests, but it can be done. It's fine-grained control. So essentially, as distribution, as dist allows you to distribute sources of your code. If you upload it to Pipey, Pipey requires the sources to be present. Now, it also includes other resources that you add to your package, but anyway, it takes a snapshot that can be built and reliably transported to another machine where it can be built and work as if it had not left your working environment. Now, there's also wheel distribution, a binary distribution. Right now, nowadays, these are equated. There used to be other distributions like MSI for Windows executables, but they are slowly being deprecated in favor of wheel because it's simpler, it's more, it is versatile, and it's supported by many, but by everywhere, and it's more compact. So in order to make a binary distribution, you just need to run this. Let me clean up the folder so that there's nothing in our way, and this one. Okay, we will monitor the folder here, and I'm running the program here. Okay, the instruction. So if after I press it, there will be a lot of stuff. You see, we've got fast primes here. We've got build because it had to build stuff, and we have a dist folder and some meta information that Python that setup script created. And here we have the main goal of binary distribution. This way, this file I can put wherever I want. I can put it in Dropbox. I can put it. It's not a good idea to commit this file to Git because this is a binary file and it changes. And the changes it reflects are already present in the code. So it is not a good idea to actually commit to commit this file to GitHub or to Git. Anyway, but another place I can post this link to my web page if I had one, or Dropbox or whatever, and from there people can download this and install it. How can this package be installed? Okay, let's copy this. Where it is? Well, it is in this. Sorry. Here cp dist, and what I have here, let's copy it to my I don't know, downloads.
Ivan, we have 10 minutes
Yes.
left, so why don't we do
How
a
many
summary and maybe answer some questions?
Okay, 10 minutes left. So the summary is it's 2 minutes. First, I copy this wheel distribution to my downloads, then I cd to my downloads, wherever, it doesn't really matter. And let's install this. Pip install, and what was the name? Example, this one. You see? Oh, let's pip uninstall first. Sorry, pip uninstall example 8. Yes, please kill it. And now I am installing it, and you see there was no need for compiling because everything has been done when I instructed Python's my setup script to create a binary distribution. Essentially, these are the essentials of how to organize your package or your project into a package, and then how to package your project, how to put your package into a distribution. So that is mostly the core idea. The materials for this seminar were collected from the plethora of documentation that Python has. So so basically these are the essentials, and those documentation is quite good, but sometimes a bit wordy and not to the point. So anyway, for example, if you build a package on one system and it has one shared object, compile package on one system, and then you want to see if it works on another system, you'll have to set up a special compiler options. Unfortunately, I can't really tell you how to do this because I have not seen the need for this particular case. It is possible, but it requires you to specify to have a special to specify the location of libraries that are compatible between if you're building on Ubuntu, that you need to specify a special library, special environment with the libraries against which your compilation can link. In order, and these libraries should also work on Arch. So this is one thing. It is much easier to set up a virtual machine nowadays where you just install, deploy Arch and use and just take the sdist of your package and compile it there. This is much easier. But anyway, of course, it depends. If the libraries are binary compatible and the system are compatible, then it will work. Otherwise, you have to specify particular versions of libraries that are needed. Of course, there are other options which mostly relate to, for example, if you use Conda on Arch and on Ubuntu, then probably it is better for you to distribute a source distribution rather than binary distribution, because Conda is it sort of ships you not only the Python interpreter, but the whole ecosystem of supporting packages and modules. For example, it is easier for you to set up the necessary building pipeline in Conda than by yourself, because Conda specifies automatically. Yes, 3 types of wheels. These are just a distinction that is made by the creator of wheels. Let me start from those which are most important. First of all is pure Python. If you make a binary distribution of a pure Python module, it will run on Ubuntu and on Arch and on Windows, because the modules are pure Python and they are shipped with their source. So. And Python also operates the same on Windows as on Ubuntu, with some minor differences, but anyway, it is guaranteed that the base language will work there. Okay, so this is pure Python. You don't need to actually, it's just a way to package your so pure Python will work in Arch and Linux. Now, platform dependent is exactly the case that was asked from me in chat. This is like essentially a binary distribution specific for each particular platform: Windows, macOS, Ubuntu, special version of macOS, and special version of Python, for example. So that's the main distinction. And universal, they are since nowadays Python 2 is is sort of legacy, and it is not actively maintained because we moved on to Python 3.9. So they are not really, that's not really applicable here. However, universal means that that this package can be, that this binary package, of course, it includes some scripts, that it is runnable on Python 2 and 3. and that's it. So that is the main distinction. So nowadays, the last universal is not widely used because we have Python 3 now, and these two are the most dominant. This because, for example, you need special libraries to run Torch on Windows and on Ubuntu, and this because at most of the times you don't need compiled extensions. So that is the reply to that's the elaboration. Now, the final thoughts on all this thing. If you want to distribute your compiled extensions without hassle, yes, use bdist. However, if you are working within Conda environment, and every environment in your machines that you have access to is almost the same, it is easier for you to compile it. But if you want, for example, yes, if you want to put your package in Pipey and make it available to the whole world, then you will most likely need several platforms in order to create binary distributions for each one of them. And well, of course, you will also distribute your source distribution in Pipey as well. So, but anyway, for each specific platform, you need to have a specific binary distribution view. Yes. You can't reuse them. They're not binary compatible. In macOS, it is ubiquitous. So the final thoughts, final minute is that just copying your an archive with your code is okay, but it's not. It doesn't scale. It cannot, and it does not have the necessary meta information for easier distribution of your package. Of course, just a simple archive sometimes works, but for larger projects, you need to actually think about how to larger projects that live longer than you maybe, I don't know, that live quite long, that have long lifespan. Anyway, so the farther you want to distribute your project, the more things you need to package. For example, if you want to copy your project into a folder, next folder, you just copy it. If you want to your project to copy to your colleague, you give an sdist or an access to GitHub. And if you want to ship your project to a colleague overseas who is a user and not a developer, then you create a binary distribution wheel for that user's platform, and the user will have a nice time using your product. That's it.